Okay, guys. So let's start lecture 18. So we're going to continue on our analog to digital and digital to analog conversion type of thing. So for lecture 16 review, so we looked at switch capacitors. We found out that what we can do is replace resistors with these switch capacitors, and there are some benefits for doing that. And we can control the current flow going in this direction or that direction, which leads us to an inverting integrator or non-inverting integrator, right here, plus or minus. We can also look at these bandpass types of filters or replace those resistors with these switch capacitors right here. And that allows us to do some really nice frequency tuning. It has to do with the clock frequency of our switch capacitors. We also looked at some digital to analog converters, the weighted resistor method, the R2R ladder method, the inverted R2R ladder, and their capacitor types of analogs right here, where you have the weighted capacitor and the C2C digital to analog converter, and also the non-monotonic digital to analog converter. So for lecture 17, we went back and reviewed the comparator that's used a lot for these analog to digital converters. And so it's comparing these two signals, and it's going to saturate them to either the VCC or the V or the negative VCC or VEE down here. So to saturate those. We looked at the counting analog to digital converter right here, the successive approximation analog to digital converter, which is using the binary approximation method. Also the Siegel ramp analog to digital converter right here, and a flash ADC. Okay, so before I go on, let's review a few things, because someone had asked a question about how all these things tie into something tangible, and why we're looking at these kind of things. So this right here is like just the wireless world. This also applies to many other things that we look at too. But you can see the types of zones for every single type of signal, right? The AM radio, remote control toys, broadcast, right here, GPS, satellite, weather, cable TV, highway, police radar, things like that. So there's many different kinds of signals, right? From radio to audio. And where filters tie into this is because inside of the devices for each of these things, they do lots of signal processing with the signals coming in. And from Fourier analysis, we know that all signals can be transformed into lots of sines and cosines, or just lots of sinusoids at different magnitudes and different harmonics, right? And inside of these devices, they're doing lots of things, like they're taking one signal, and I'll just describe it by a sinusoid, right? But it's really a collection of sinusoids. And so the actual signal may look quite different, right? But it's just a collection of sinusoids, right? So that goes in, and then they may scale the frequency, like shift the frequency up or down. And when it goes through those components, where you take when you look at your spectrum, and then you shift it up and down, what happens is that, so for example, if this went through a modulator, and you have another signal coming in here, well, what happened is that the output will be, some type of spectrum, right, of your signal, and it'll be shifted to the right and to the left, right? So you have another signal over here that's a copy of it, right, to the right and left. Well, what happens is, depending on how far that is, you may actually be going into another band nearby, or your device may interfere with another neighboring device that's trying to get a clean signal. So you don't want to do that, right? So you need to get rid of these guys right here in the end. So what you typically do is you send this through a low pass filter like that. And so what happens, like this is 0 frequency, here's like some other frequency out there, right? So what happens is you will filter out these frequencies here and here. So this frequency over here is negative. So here's like positive frequencies and negative frequencies. And when you see like negative frequencies, it just means that instead of going around counterclockwise, just think of it as going around clockwise, and that's like the negative frequency. Okay, so you can think of it like this for your low pass filter. It's like, this is just a mirrored copy of it around this axis right here. But you get this frequency, and that's the one you want to pass through to the rest of your components in there, and then you get rid of your other one so it doesn't interfere with other electronics in your system and also other devices that are nearby. So that's really that's one example of the low pass filters that we've been dealing with. Also, there's other things too, like inside of these devices, they may have a super heterodyne, and what that'll do is that will take your,
So that's not a band gap? That wouldn't be.
Oh no, no, because this is 0 frequency right here. I know if you look at the whole thing, it does look like a bandpass, and you can even think of it as that, but it's.
Is it like 0 hertz or just 0 frequency?
Yeah.
So you have a signal
0 radians per second, huh? Yeah. If it makes more sense, you can just think of it like this.
Mm-hmm.
But you know, for people who like do this stuff, who make these kind of devices for RF types of systems, they think of the entire spectrum. So, so this is just the frequency spectrum in its positive and negative. But the negative side just looks like a mirror copy of the positive side. Yeah. But yeah, so that's why this is a low pass, but it looks like a band pass when you mirror it. Yeah. And also like the super heterodyne, what happens there is that you may have some components of your system down the way where you need to do some initial processing, and your signal comes in at all these different frequencies, right? And then it needs to go through a super heterodyne, which outputs your signal at one particular frequency that the rest of your devices are a perfect match for. So that's what that's for. So just like radio stations, you know, it'll come in at one frequency, right? You have to detune it or tune it up or tune it down to the frequency your other components are tuned to and tuned to operate at. So it's one frequency for everything after that. So there's going to be some shifting in frequencies that you have to do, and that's where the filters come into play every time you deal with those kinds of things. And also dealing with noise, you want to filter out the high frequency noises. Yeah.
So is that 0 relative to the frequency that you're interested in, or is that actually? I guess I'm confused how you have 0 or.
Oh yeah. Well, it could be either.
Okay.
Yeah.
Gotcha.
Yeah. You have to be either. And it has to do with shifting your frequencies.
Gotcha.
Yeah. Yeah, but there are also just like whenever we mention DC, you think of it as like a 0 frequency.
Mm-hmm.
Yeah.
Gotcha.
Yeah, and oh wait, I got a few other things too. So so this right here is like an example of, it's a single sinusoid, right? And so how that relates to our J omega, because it's like, you know, we have this this complex frequency we're always dealing with. You could think of this as, if you like took a snapshot in time, that's the angle, right, that it's making. So this is like the magnitude of this, you know, going around. Right here is 1, the magnitude is 1. But your omega t is the angle that's being traced out. And so it's always going around like this, right? And you're like taking a snapshot and looking at the phase, right? But as you can see, that comprises a sinusoid. And mathematically, it's really easy to deal with and think about. That's why we're dealing with these j omegas, because we're converting everything to a series of sinusoids that we play around with, we filter. And that's why on the Bode plot, we're always looking at what's being filtered, what's being amplified as a function of frequency, because everything's coming in. We're thinking about it in terms of frequencies. Okay. And here's some figures regarding harmonics. So this right here, think of like, it could be any kind of instrument, but think of like a guitar, right? It has, you know, these different frets here for your guitar string, and so if you just pluck it, you know, that's like the fundamental frequency right there. But you could put your finger down on a fret, and then you'll have this other frequency right here. But if you think about it, these frequencies, they will have different harmonics, right? Because if I have, let's say one node right here and another node right here, and this string is able to vibrate back and forth, you could also see that, well, other types of waveforms can go in there as well that also have this node. You know, for example, you know, you can have this one, right? It also has those nodes, except it's now moving at twice the frequency, or 3 times the frequency, or 4 times the frequency. You can have many different types of things that match up with that, and those are the different harmonics. And they have different magnitudes, right? But that gives the sound its characteristics. And so, for example, if you look at this, well, all of these have like the same magnitude, but if you add all this up right here, the composite waveform looks like this. It looks very different than eating one of those singled out. But that's how the actual waveform looks. But it's just, you know, composed of different types of sinusoids. And in this case, they all have the same magnitude, but they're at different harmonic frequencies. You know, omega, here's like 2 omega, 3 omega, or 4 omega, and on. Now, when it comes to other kinds of things, when you're looking at the sizes of these changing, that allows us to determine different kinds of sounds. For example, this is like a very simple tuning fork. It has like a very simple sinusoid. But here's a flute, here's a violin, and here's a singer. Now, they can all be singing or playing the same note, but we're able to tell which one is a flute, which one is a violin, and which one is a tuning fork, simply because each of these right here has a different amplitude for that particular frequency. I mean, that particular sinusoid. So one way to think about that is on a, if you look at the frequency response, where this is frequency, this is the amplitude, not gain, it's just amplitude, right? You'll have, if you look at the spectrum, maybe you have some fundamental spectrum right here at omega. Maybe at 2 omega, you'll have that. Maybe 3 omega, something like this. 4 omega, yeah, something like that. And those are just the amplitudes. So if you did it in 3D, you would have time on this axis, right? And this would be the amplitude of that sinusoid contribution. So if I were to, you know, plot this out in the 3rd dimension, it would be a sinusoid at that amplitude, you know, looking something like this. Right? And then this one right here would be also, you know, a sinusoid, but it has like a smaller contribution, a smaller amplitude. All right, Well, that frequency is higher than this one. It doesn't look like it on my plot. But you see here, when you're looking at these harmonics, this line spectrum, you're looking at the amplitude of that sinusoid contribution. That's all you're looking at. It's the amplitude of that. Now, of course, when we do like a Bode plot, and you have this frequency here, now we're looking at gain right here, right? So output over input. And now when we do, send it through, something that looks like that, or, whatever our Bode plot is, this amplifier, what happens is that, well, certain of these harmonics are going to be attenuated, some are going to be amplified. Okay, then you can change what this thing behaves like, or you could use it to pick out certain frequencies or clean it up. But you're processing that through some type of filter that we can create in this class. And that's where these things are. Now, of course, you see this other stuff right here, so it's not ideal. It's not like these single nice, lines here. You have these other components, right? And this is a log plot right here, so, but a lot of this right here is noise. A lot of it has to do with things in the room, things in the instrument itself that's, causing other harmonics that's, and it's causing other frequencies that are not harmonics, right? But it's the main ones that are characterize that particular sound. If this was a synthesizer and you're trying to synthesize a flute, what you would do, you would look at the spectrum, and then you would say, okay, well, I need, this line, these particular lines, and it would sound like a really sterile, clean flute if you did that, because you're missing out on all the noise and all these other messy characteristics. But for humans, they sort of like that. It's more pleasing to the ear when we hear things that are kind of messy. There are people even who like the old kind of music where we use like analog tape instead of digital, because of that reason too. But yeah, so another thing is this. So I told you before that because of these sinusoids, if we add them together, we can create all kinds of signals, right? And last time, if it was just one simple sinusoid, we saw that it can make a circle, right? But if you have a really complex combination of lots of sinusoids added together, you can make other things that are totally unlike a circle, right? So can anyone guess what's behind that block right there? A square? Is it? It's something you all recognize. I'll say that. It's not a circle, it's not a square. Not even a triangle.
Hexagon?
Nope. But you can see here that, this piece right here and this piece, they're all connected together and they're tracing out a shape, right? And of course, lots more is happening on this axis than this axis, right? Okay, so I'll show you what it is, because no one has guessed what it is. It's pi, right? So this shape right here, Fourier series can be used to make all kinds of signals. Any kind of, just about any kind of signal. Really sharp corners are really hard to make with Fourier because you got this Gibbs phenomenon. So, like if you're trying to make a very perfect, a really nice square wave, you're never really going to get it because what's going to happen is that you have these little peaks that pop up at the ends right here by the Gibbs phenomenon, and there's like a minimum value that it gains, but there is a limit. Okay. But otherwise, you can make all kinds of other shapes. And in fact, I have this video I want to show you guys where this one guy, Subi, made an even more complex kind of shape. So this is like a YouTube video right here. I had showed this before in my other class, so it's kind of neat. Where's this now?
Thermal motion, particle physics, things of that nature. Sine waves are important. But for my money, the coolest thing about them is you can add them together to do other things. Which sounds simple until you realize this
Does it sound coming out?
You know, right? Physics was one. My buddy Brady here
That's cool.
about that.
Okay.
There's some fancy math that I learned at the university.
I didn't know how to control the volume.
Series. These are my old notebooks. And check this out. The teacher
Is it on the
challenged
little
us
screen
to
thing?
create this
Is
graph
it on the
by
little
doing
screen
nothing
thing?
but adding together
Is that what you're talking about? Yeah.
Oh, the volume?
here. And it took me, it looks like 4 or 5 pages. Yeah, it took a lot of pages. And I ended up with this. I was able to make the graph by adding together a bunch of waves. And to demonstrate that, I created this kind of triangle.
It's the imagery that is important. If you guys can hear it. So let me, it's 8 minutes. But,
the closer the function.
okay, so see what he's doing right here?
We're gonna call these wipers.
Oh wait, let me back it up a little bit. Okay, so see what he's doing right here? So this thing right here, this is like 2 sinusoids, right? You have, I mean, not 2 sinusoids, but 2 of these right here, where you're looking at some A, then E to like the name, let's do J omega. Okay, so each one has its own amplitude, right? And each one has its own frequency. So this right here, this J omega right here is the theta, the angle that's swept. And it's just adding together. Because you know how I like to add vectors, right? If you have like this vector and you add it to this vector, all you do is take this and put it right here. And so your resultant is this vector right here. So that's what's happening. The thing is that this vector is moving around in time, and this vector is moving around in time. It's attached to the end. So that's what's happening here. And so it gets more complex. But that's just 2 things.
A basic list. What are we going to call these? Wipers? Nope. It's wipers. Okay, so we're going to add a
Okay, so
wiper.
I'll just fast forward a little bit.
By doing that,
But
graph the
this guy
function.
right here, he's a student at Georgia Tech, and so he played around with this, and he made it like a little more complicated. And he's going to try to make something to
It's a
trace out
hard
that.
image to draw using math. It's got curves, right? It's got little sharp points and switchbacks. It's self-serving for me. So this is an appropriate challenge for somebody that's demonstrating math swagger. The problem is he actually can do it. He can model this using nothing but circles in the Fourier series, which is completely impressive. Check this out. The first thing that he has to do in order to draw this image is to extract the x and y positions that he would need to make functions for in order to make this thing work. He then needs to create a Fourier series for each one of those functions so that he can add them together. And as you can see, these first few were not winners. Like no stretch of the imagination could make your brain think this looks like the side profile of a human head. Everything's a bit derpy.
That's why Fourier series needs more
And he adds more
terms,
ways
you know, to get things right.
Things start to hone in.
It gets better.
Starts to look really good. And about 40 circles in this whole function, things start to look really good, and your brain would totally think.
I mean, look at these right here. There's a lot of things. Each have their own amplitude, their own frequency. They're going wrong.
But it's not. It's complete order bound up by a mathematical function. In fact, this is why I love math. It's the language that describes the entire physical world. We can approximate anything as long as you have enough terms. This is the beauty of the Fourier series. You take
Okay, so
things
anyway,
you
that's-
understand, like oscillators.
Yeah, so that's to give you an idea of why we're always dealing with frequencies so much, and why they're so important, and all the things that we can do with them. I mean, even in communication, like if we have an antenna here, So let's say this is the antenna, right? It's going. This is a very simple type of way to think about this, but it has this electric field, right, that comes in, and it has, and you can describe it in terms of some sinusoids, right? But this field, is coming in. It's going to interact with this antenna, and so this antenna has charges in it, right? And so when these little guys, little charges here are just hanging around, not doing anything, all of a sudden this signal starts coming in, and so this field starts modulating the positions of these charges, and they follow that field, right? Well, that right there is a signal that can be picked off and processed and amplified using the things we're doing with this in this class. So communication, signal processing, even image processing uses a lot of these methods as well. So lots of important things that this could be applied to. Okay, so also any more questions about this kind of stuff? I'm just trying to make it like a tangible kind of link to things that you guys are kind of somewhat familiar with, like sound, right? Okay, good. Okay, so more on, so we'll finish up the ADZ kind of stuff. So this right here is a dual ramp method. So we did a single ramp last time. This is a dual ramp method right here. So you have your input signal coming in, you have your reference, and so what's happening here is that it's being integrated, and so, and then here's the comparator, and here's your logic control. So it's kind of weird, but what's happening here is that the input, when this switch is closed, what's happening is that this integrator is going like this, uphill like that, over some period of time, okay? And then once it reaches a certain point, at the end of its travel, then all of a sudden the switch goes this direction, and then the current goes the other direction, and then this starts falling down at some time. And so what you can do is, since they're all going up and down at the same value of that integral, you can set these two things equal together, right? Here's like the overall RC of the system right here. And then you come up with this relationship that the input over ref has the same ratio of n over the maximum value here. And also, you can see here that if you look at the times, you also have this ratio. So what you can do is, I mean, yes, it is kind of slow because you have to wait for this to build up and then wait for it to discharge right here. But it is another type of analog to digital converter. And then from those times alone, you can figure out what n is. And here's, this is the last method right here we're going to talk about. So this is called the delta sigma analog to digital converter. And it's even weirder. But so this delta sigma converter, they're widely used in today's integrated circuits because they only require a small number of precision components, and they're easily implemented in switch capacitor form. Okay, so they're ideal for digital signal processing applications. They're used in audio processing, high frequency signal processing, and mixed signal ICs and integrated circuits. So what happens here is that your signal comes in to this, and then you can see this feedback, right? So the difference between these two signals is what's being fed into the integrator. Okay, so you're integrating, you can think of it as integrating the error, or you can think of it as integrating, just the difference between two signals in time. And then what comes out of here, you take that from analog to the digital domain, and then you feed that out, right? But you also take off that signal and feed it back, right? So what this piece does, it's in the digital domain right here, so the feed it back, go from the digital back to the analog to mix it into the signal, right? But what this piece is doing its correction, right, of what has been integrated there. So, it's kind of hard to visualize this. Okay, let me try to do it like this. So, because integrating a voltage and time, you made me think like, how does, it's hard to get a feeling for that because you're not like really sure what that really means tangibly. But if it was current, and you integrate current and time, you get charge, right? So let's say let's say the signal is current and you're integrating current to the voltage. So let's say you're trying to give a particular type of current here, some value of current, and then your input is like all over the place, right? And you're trying to get some type of some value of charge. And so the question is, the value of charge you want is this value, right? And the current's all over the place that's coming in. So what you can do is, if you integrate this signal, you can find out exactly where you are in charge on your capacitor or whatever you're trying to charge up, right? If you're too high or too low. And so the ultimate difference between what you want and your total integration of all that charge tells your system what it needs to do going back in. Does it need to, it's sort of correction that it's feeding back. If your charge is too high, then that difference is going to try to subtract that. If it's too low, it's going to try to increase that. Okay, so that's one way to think about it.
What kind of ADC is used internally? Like, this is an ADC with an ADC inside of it, right?
Yeah.
Okay, so they just choose any ADC that they want, or is it a certain?
Well, yeah, so in the example they're giving in the book, it's 1 bit. It's very imprecise, it's 1 bit. And yeah, so what's happening here, and I'll show you the system in the next slide, or 2 slides later. What's happening is that you're really looking at the average, right? So the average output of this, this is gonna be weird, but okay, so this right here is 2 bit, so it only has 2 states, and the states are positive VREF and negative VREF, right? And you're thinking like, how is that going to equal whatever this is? But what they're trying to do is say, well, if you average it out in time, how many positive VREFs and low VREFs, you can get the average of this to equal that.
So is this ever done with an in-bit like you've shown? Because I'm asking because the delta sigma DAC does it by pulse density modulation, so it's always 1 bit. So I thought delta sigma just meant that it was a 1 bit integrator essentially.
Oh, I'm not sure about that.
Okay.
Yeah. I'm not sure about that. Hopefully we'll get to those kind of things. But so far, the book is presenting this as the simplest type of introduction to the delta sigma. And what I think is happening here, why they call it the delta sigma, I think that part right there is a delta, and you can just consider that as a sigma. So you have the difference right here between these 2 things. That's the delta, and you're adding them all up together. That's the sigma. I think that's why it's done that way. The book didn't really say. But the integrator right here, it accumulates the difference between the VX and the DAC output. The feedback loop, it forces the average of that DAC output to equal this. So this is what you're getting out right here. And the sample rates for the analog to digital, this part it's actually oversampled. So it's like 16 to 512 times the Nyquist rate. And so it's called an oversampled. And to remind everyone what Nyquist is, that Nyquist rate. So if you have a signal, like let's say you make a sample here in time, another sample here in time, the sinusoid that you can fit there is like that, right? And so what you try to do is you try to make your Nyquist rate greater than twice your highest frequency that you're trying to sample at, right? And that's why, like for audio, human hearing goes from like 50 hertz to around 2200 hertz or kilohertz, and that's what we can hear. But as you know very well, like in your digital audio, it's being sampled at like 44 kilohertz, which is twice that, right? So that's the reason that's done. Now this is being oversampled. I'm not quite sure why it's oversampled, but that's what's typically done. There's some decimation here, and so what's happening here is that you're doing some downsampling, where you're not sampling everything that's coming out. You're like sampling, like maybe every other or every nth time you're making a sample. So there's some decimation there.
It's oversampled because you have 1-bit accuracy, so you have to, since the decimator integrates, or it averages the output, so to get a frequency, or a Nyquist rate of 2 to the n, you have to sample that many times more. So if you want an 8-bit output with a 1-bit input, you have to decimate by 16, or 255. That's why you
Okay.
oversample on the first stage and then you decimate later.
Okay. Okay, thanks. Okay. So the okay, yeah, so it's set down already. So this is what it looks like if you wanted to see what the components are. So here's the integrator. Here's the comparator part right here. It has this D flip-flop. Yeah, the reason they have the D flip-flop is for, so you have this clock rate right here, and so what's happening is that this flip-flop will change only on the rising of the clock state, right? And so until it rises again, whatever change happens, it won't really take place until the next rise. Okay, so that's what it, so it has some memory for that flip-flop. And here's the 1-bit DAT coming back. It has 2 states, the VREF and the negative VREF, which you mentioned. Okay, so yeah, so I already mentioned this right here about the 1-bit DAC. Yeah, so this right here, the purpose of this is always trying to correct this toward a 0 delta, a 0 difference. It never really gets there, but on average it does, right? So, so it's not super fast, but it's really quite useful for many things, as we mentioned before. So this right here can be replaced with the switch capacitor version, where this component, this section right here is that, and this portion down here with these switches correspond to this right here. Okay. Now also, when you're sampling things coming in right here, a lot of times what people will do is they'll put a sample hold right there, because what they don't want to happen is that as you're doing your conversion, your signal changes, right? So like here's like the input signal right here, right? So what they'll do is they'll sample this, right? And so this signal will remain about at this level, right, until they decide to sample again. So it holds it right here, and then they sample it again. But a couple of problems with that is, first of all, there's going to be some leakage. So whatever value you get, it'll eventually drop a little bit. And also, depending on what happened to the signal during that time, it may take a little bit of time to get up to the right value. So you have this acquisition time. You have to try to tune that depending on how fast your signal is moving up and down. For a few examples of what these things look like, here's the simplest version right here, right? So your signal comes through, your switch can close, then now get to that particular voltage, right? And it'll hold that once you open that up. That's one way of doing it. This right here is the buffered method, where here's your signal, and then that is copied over here, and then that goes to this capacitor, which is held, and then that's buffered over here. This is the closed loop method right here, where you have this, where you have your input signal, right, that's coming over to here, which is copied down here, is held right here. You have this switch. So once that opens, it holds it. If it's closed, it drains it through here. Then you have this integrator method. Yeah, so for this integrator method right here, your signal comes in, copied here. You're able to come over here where it's treated sort of like as an integrator, right? And then you have to switch to, that's also here too, to drain it out. So, okay, so those are the basic methods for the sample and hold. So now we'll get to oscillators. Okay, and also amplifiers are used for oscillators too. So oscillators are used for signal generation, and we'll consider sinusoidal oscillators based on op amp, but there's other types too that rely on inductors and capacitors. So op amp oscillators can be used to generate signals with frequencies up to approximately 1/2 of the unity gain frequency, FT, of the op amp. And it can be described by positive feedback. So in this case, we're using positive feedback instead of negative feedback, which we've been using for a very long time. Okay, but you need that. And another interesting thing is that your input here is 0, right? So you have 0 input. You have this feedback, right? And it's being amplified. And there are some conditions on this feedback as well to make it oscillate sinusoidally. But your output, of course, is your sinusoidal signal. Okay, so so this right here is a frequency selective feedback. So that's used in oscillators designed to produce the output even though the input is 0. For a sinusoidal oscillator, we want the poles of the closed loop amplifier to be located at frequency omega, the one of our oscillator. And that's going to be precisely on the j omega axis. And for positive feedback, that's used to sustain oscillation. So here's what it looks like, the feedback. And right here you can see that instead of it being positive, ours is negative now for the positive feedback. And here's what's the condition of the denominator right here. So you got to have this condition, which means that that loop gain is 1. And for the last thing we like to talk about here is, in order to get that right here, you have to have these 2 conditions that are necessary to satisfy that. And it's called the Barkhausen criteria. And it means that your angle of your loop gain, that has to be 0. And also your magnitude of loop gain has to be 1 for sinusoidal. If it's larger than 1, then you'll get some distortion. Okay, that's it for today. See you guys on Monday.